Sure, fine.
Okay, thanks for that, Simon, and thanks everyone for tuning in and for the honour of talking at this. I've met Eric a few times. We hosted him down here at Melbourne when Simon had him over for the neotoma workshop. I met him a few times at conferences and quite a number of times over Skype. It would have been back then, trying to iron out the wrinkles in my brain about neotoma, which always turned out to be about my brain, not about neotoma. Tilia. And uploading and being a data steward, which I must confess has gone in one ear and out the other, but I'll keep working on that. So thank you very much for this honour. I'd also like to acknowledge that I'm on Wurundjeri country in Melbourne. I'd like to pay my respects to all the elders, past, present, and those who will carry their knowledge on in the future. So I want to talk to you. I'm not going to get too magnetic here. I'm not going to delve into what has turned out to be potentially murky waters of the global resonance of the Lachamp event in terms of biological implications and all these sorts of things. Because I think first and foremost, we need to characterise the event. We need to understand whether it is a global signature, and we need to know its footprint, for want of a better word. So I'm going to talk to you about some work we've done in Tasmania, and as I'm kind of waffling here, I'll play this video. I won't play it all the way through, but about this really remarkable site. Well, I think the size of this video is potentially causing some dramas, but we'll see if it kicks off, and I won't spend too much time wasting on it. So this is a site that was cored in the late 1990s, by Eric Colhoun and others, using a Macroth corer in which they retrieved about 3 meters of sediment. And they subsequently analysed it and did some sort of preliminary radiocarbon dating, attempted some uranium thorium dating of the very organic rich sediments to try and understand how old it was. Really only the radiocarbon dates worked, and there were 3 radiocarbon dates that ended up underpinning the record. Then they used matching of the pollen sequence to regional climate proxies, in particular Antarctic climatic change, to propose that the record covered the entire last glacial cycle from isotope stage 5E through to the present. This is a site in Tasmania, which is a really, really important site, not only for regional conversations about landscape use. This is occupied early by Aboriginal people around 42,000 years ago, 43,000 years ago, and they've had a profound influence on the vegetation landscape. You can see here in this video, there are pockets of rainforest surrounded by treeless vegetation. It might remind people of the moors of Scotland or other sort of treeless areas that have also been argued to be contributed to by people. There's a lot of lakes, so it's really suitable for what we do. It's sitting in the mid latitudes at about 42 degrees south, between 40 and 44 actually. So it's sticking itself, a mountainous region, into the zonal weather patterns that encircle Antarctica and impart a very southern climate signature. So it's important for conversations around human impact on landscapes, but also regional and global climate. This is just a drone. Sorry about the jerkiness. It was early on in my droning days. You guys are getting that right now, actually. Here's the site and its sort of geoposition. It's surrounded, it's located within these circumpolar zonal westerly airstream that encircle Antarctica and are really remarkably symmetric, not only in the modern day, but also over longer periods. Here's where it is, and here's where it's located amongst a bunch of other lakes. Now, the initial pollen record from this, as you can see, had essentially 3 reliable radiocarbon dates, but there were some really big shifts between trees and shrubs, okay, and grasses and herbs. And the sequence here was really reminiscent of what you see in Antarctica. And I'll show you that in just a moment. So this proposed Eric and others to wiggle match, if you like, in a kind of visual sense, the record to the Antarctic sequence. I followed this up with some work using pollen transfer functions, and you can see the top plot here on the left, as it's just Tasmania again. Top plot here on the left shows pollen inferred temperature change from Lake Salina and how it oscillates through time, and there's a broad match between what happened in the bottom curve there, which is Vostok in Antarctica, and also oceanic sea surface reconstructions from the region. But it's not perfect, and there's, it's been one of these thorns in the side of long, continuous late Pleistocene records in Australia is the ability to date them, not only in Australia, but I imagine globally. But there are no volcanic ashes in this region that allow us to tie things in synchronously with volcanic events or other kind of useful means of dating these things other than by wiggle matching. So we recored the site. We ended up getting 6 meters out of it, not 3. So we're really excited. And here's a paper that we've just published, this year, where we combined radiocarbon dating, also lead-210 in the very upper bed, optically stimulated luminescence, wiggle matching, and paleo-mag. And what I really want to talk about here is the critical role that Lechonck and paleo-mag played in being able to have confidence in this age model. And I'll show you what we can do from then on. And so here was our age depth model, which was based on radiocarbon in the blue dots, optically stimulated luminescence in the red dots, or the red marks. You can see here we abandoned the radiocarbon because there seemed to be plateau effects, but not your usual one around 40,000. There was also one here around the 20,000 mark. So already we're introducing some kind of complication in this that you could pick apart, if you like. Or why didn't you choose, maybe the OSL's wrong, or why didn't you choose other trajectories, and all of these sorts of things. So we're a bit plagued by being able to get a robust chronology here, which meant that this beautiful pollen record that we devised, which whilst on the left-hand side, and I'll put this in purely in homage to Eric and Tilia, on the left-hand side, you can see there are these shifts that, putatively look like shifts between cold climate and warm climate that may or may not mirror what we see in Antarctic records. And there's also in the Holocene, the arrival of a whole bunch of plants that we can consider as anthropogenic indicators. So it's a really important record here about human impact and paleoclimate. We noticed a superficial similarity between geochemistry. Okay, and on the right-hand side, the blue line here is lead over aluminium, and the mountain just above it, this site was touted as a lead mine. So we're thinking this is during cold periods, a devegetated landscape and allowing weathering of the rocks, which corresponded, we thought superficially, to dust being blown into Epicodome C in Antarctica. And it turns out when we wiggle match this using an independent program, there's a really strong correlation. So we feel pretty confident in this core on the right-hand side that whatever's going on is tracking climate over the long scale. So we're confident that we could use climate to constrain the chronology, but we didn't want to depend on it all the way through. We wanted something independent, because if we start talking about climate, then we're using climate to train the record's age. We end up sort of in a bit of a circular argument. So we characterize on the left-hand side the kind of sedimentary facies that are in this. And this is work done by an amazing colleague of mine, Agat Lissé-Pronovo, did all the sedimentology and the paleo-mag work here that really got this going. We found that there was a clear difference between glacial sediments and interglacial sediments. We ran all these paleo-mag analyses, which I won't expect you to understand, but on the left of the right-hand side are raw data, and then if we correct for sedimentary processes and all those sorts of things, we get what we consider the signal that we can use to maybe identify shifts in paleo-mag or shifts in the magnetic field. We also used beryllium-10, which can be the product of changes in cosmogenic rays bombarding and hitting, I think, oxygen and nitrogen in the Earth's atmosphere. And this can also, in combination with this paleo-mag data, be used to track changes in the geomagnetic field, given the role of the geomagnetic field in protecting the Earth from cosmic ray bombardment. So here's what Agat came up with, and we found that there was a nice excursion across all of these relevant proxies that speak to geomagnetic field. at two particular depths. A really strong one here, which timed with our OSL and our C14 record to spot on the Lachamp excursion, 42K. There was a secondary one, or a later one, which I think came out at around 32, between 32 and 26, which, whilst not present in a strong way across all the proxies, does correspond to hints elsewhere in the globe to something going on with the magnetic field there. So I'm mentioning that as this record and other records in the region that cover this period might be useful for mining and characterising some of the lesser excursions. We also found, and I'll show you a potential for the Blake excursion further down. Okay, so this gave us some really nice confidence. Here's the Blake excursion here, potentially, a single point here in the inclination, but it requires a lot more work. Okay, it times really well with our climate-derived age model, but we haven't used it going forward, but it's just one of these tiny little hints that maybe there's something going on. So then we produce this age model where essentially the black up the top here is C14, then it moves into OSL. The red line is deriving an age model which brings in the Paleo-Mag and the Beryllium-10. The green line is one based solely on matching the geochemistry of Lake Salina to the Vostok record, so the Epigodome C record, and principally the lead over aluminium and the dust in Epigodome C. And we're really happy that they all converge within error to agree. There are some points there through the period between around about 20,000 and 80,000 where the green climate-derived line maybe exceeds the error ranges of the other two methods, but they all agree pretty well, and particularly on where the Lachamp is. So the fact that we could anchor this age record with this known global event, which showed up very strongly in all of our Paleo-Mag and Beryllium-10 data, gave us a lot of confidence to use this model down through the core. And is actually the first, I believe, and maybe people can correct me, and again assures me it's the case, the first unequivocal recording of the Lachamp in Australia, on terrestrial Australia. So it's pretty important, not only in Paleo-Mag, it was also useful for this record to give us confidence in the age depth model, which enabled me to shift the pollen record, if you like, to age, and that's what it is now. The red line there is the arrival of Aboriginal people into Tasmania once the Bassian Plain, the sea that separates Tasmania from mainland Australia, was low enough through the last glacial cycle for people to cross. And the little dash line above that is 17.8K, which is the timing of the termination of the last glacial maximum in mid-latitude southern hemisphere. So we're getting some really nice concordance there, but that's within the radiocarbon period. How does it work out with the deeper time stuff? There's really a big effort to understand. I mean, given that the Australian landmass was occupied so early by people who are already expert users of fire and very skilled. I mean, humans evolved with fire and have used fire all throughout the evolutionary trajectory over the last 2 million years of hominid evolution. So skilled fire users arriving into a flammable landscape. And there's a lot of debate over what the influence was of people on the landscape. And they range from skillful mastery and complete modification of the landscape through to benign, quasi-parasitic arguments where people had no influence whatsoever and just sort of mimic what they saw in nature. So these are very important topics that move beyond science into the political realm quite often. So using the old Lake Salina data, this red kind of multicolored plot in the middle, this paper proposed that there was no influence of the arrival of people on the vegetation from the only continuous record that stretched through this period, and built a narrative about landscape change of people and their role in the extinction of megafauna. If we look at this new record, and the top plot here is when the Bassian Plain was traversable, okay? So this line here is that point of ability to cross. So we can see way back here, 150,000 years ago, you could you could not cross into, so you could cross into Tasmania. Then there was a long period of flooding of the Bassian Plain. Around about the earliest evidence for arrival of people into Australia, 68,000 years ago in the north of the continent, there was a period of time, supposedly, from reconstructions where you could cross into Tasmania, but we don't see any archaeology, which is the next plot down. It was not traversable again for a period of time until around 42,000 years ago, 43,000 years ago. And we see immediately upon the availability of the Bassian Plain to be traversed, we see archaeological material being found or recorded in Tasmania, and people arrive. So how does this influence the vegetation? So what I've done here in that fourth plot down, the Poaceae, the grasses, I've extracted that data from the full data set, converted it into standard deviations from the mean, z-scores, and highlighted in red anytime that the curve exceeds more than 2 standard deviations from the 270,000 year mean. And you can see here, right synchronous with the arrival of people, there's more grass in the landscape than there's ever been through a glacial period. And then following that, the termination of the last ice age in Tasmania, that means grass has disappeared and typically rainforest moves in, but that didn't happen following the arrival of people. And you see that third plot along here, this one here, you see a novel ecosystem that had not been there for the last 270,000 years appearing. And that is an ecosystem, that treeless stuff that I showed you in that video at the start, which requires fire, okay, and is the antithesis, if you like, of rainforest, which dominated in previous interglacials, which is extremely pyrophobic or hates fire. So we can see that this, being able to confidently date this record and analyse at a high resolution the pollen and other data, really based on, and the confidence here is that Lechamp was able to tie those age models together, has given us the power to revisit and reimagine the role of Aboriginal people when they arrived into this landscape. And here, age is running the other way there, and those coloured histograms are C14 ages of mammals that are now extinct, large mammals that are now extinct in Tasmania. You can see there that change, and I've superimposed at the bottom there the grass plot, which is red above 2 standard deviations. There's a pretty clear relationship there between, I don't know if it's causal or not, and then now that we've got the Adams event rolling into our imagination of 42 Ka, who knows what the causal link here is between the disappearance of megafauna and landscape change in Tasmania. You can see those coloured histograms disappear, and that's the disappearance of certain megafauna in Tasmania. In nearby caves, I must comment, to Lake Selina. And the other thing I want to finish on is that this allows us to tackle some paleoclimate records. In the bottom there, I've just got an ordination axis score, the principal ordination axis score from the pollen, which is just a summary of the pollen. You can see that matches pretty well to the top plot here, which is temperature in Antarctica. They behave pretty well. So it's climate-driven vegetation change overall. But you can see here through stage 6 that there's a warming recorded of southeast Tasmania, which is over here, and Lake Selina is over here on the west. Hopefully you can see my cursor. That isn't recorded in Epigodome C, but is recorded in the pollen. So there's potentially we can get at some kind of decoupling. When does the south of Australia decouple from the Antarctic signal? What are those? Are they local effects? Is some regional driver? All these kinds of questions that have been opened, the possibilities have been opened up upon, I would say, because of the strength of our confidence moving forward in being able to tie our age models and have confidence in our age models. And sure, it's unbounded and wrapped into climate beyond the Lechamp, but we have confidence because of the overlapping within our age models that we're on the right track. I think that's about 20 minutes, Simon.
Okay, thanks. Yeah, I think if people have questions, they can put them in the question box